All right, welcome to what I anticipate to be our final episode for the chapter. It's another example. Again, we're going to work through it every which way. So let's go ahead and start. Suppose we're rolling a pair of dice, and if you roll a 7, you win. What's the probability that you win at most just 5 times out of 30 attempts? Well, first of all, let's talk a little bit about probability. You got to determine the probability of success here. And that's true if you're doing binomial or if you're doing the normal approximation. You've got to know the probability either way. So the probability of getting 7 across 2 dice is, I think, 1 out of 6. I've got dice 1 listed vertically here, dice 2 horizontally, and the sum of all the values listed here. And I think there's just 6 times out of the 36 that you can get a 7. So it's 6 out of 36, or 1 in 6. That's our p-value. All right, well, that's taken care of. That necessarily means that q is 5 over 6. And, oh, that's a typo. N needs to be 30, because we're doing 30 attempts. And so to find the probability of getting 5 or fewer successes, I would have to use this formula not once, not twice, but 6 times. I would have to run it through first to find no successes whatsoever, and then do it again for 1 success, and then 2 successes, and then 3, and then 4, and then 5, and then add all of those numbers together, and that is how you would get the probability of 5 or fewer successes. And some of you might be saying, well, there's got to be a better way. Well, for this part, by hand, no. In fact, if you can come up with a good way to do this by hand quickly, do it. Write a paper on it. You will be published and possibly famous. It's quite difficult to add quickly a lot of binomial distribution stuff. In particular, this piece right here. If you can do a lot of sums of those quickly, you'll be internet famous, if not math famous. Anyway, fact of it is, you would have to do it 6 times by hand. I'm not going to do it, and I imagine you're not either. So here is where we could do the normal approximation instead. We're going to find mu, and it's 5 here, right? It's 30 times 1 over 6. We'll find sigma, standard deviation, NPQ. It's about 2. But I'm not going to call it 2. I'm going to give myself all those extra decimal places so that when I compute z-score, it will be as accurate as humanly possible. Now, before I do z-score, I've got mean, I've got standard deviation, but I also need an x value. And I'm going to take x to be 5.5. Why 5.5? Because as far as rounding is concerned, everything under 5.5 would round down to be 5 successes. So that's why I'm picking 5.5 there. So I run my z-score. I get a z-score of 0.24, and I went ahead and looked it up on the z-table for you. That has a probability of 0.5948. So almost 60% of the time, you are going to win 5 or fewer times. That's how that works. So not great odds, right? If you wanted to win a lot shooting dice, it doesn't happen. Go figure. Now we'll use some technology real quick. Right, N is 30, P is 1 over 6, Q is whatever's left. Normal distribution with the mean and standard deviation. Binomial distribution with the number of trials and the success probability. And we have here Desmos being happy to do 0, 1, 2, 3, 4, 5, all those separate probabilities added together, and it comes out to be about 61.6%. Compare that to the 59.7% we had earlier. So is it a good approximation? Yes. Is it a great approximation? Nah. I mean, it's not perfect. It's arguably better when it comes to doing it by hand, but no matter what, just like in the last section, there's going to be errors. You're going to be off by a little bit, and that's fine, right? That's fine. This is an approximation. It will always be an approximation. And this is how you can do that approximation. So you will do some practice on this, and that rounds out the chapter. We'll do some different stuff in the future. I'll see you then.